Nowadays, all modern transmitter, okay, these days, all the data is available in the digital domain. And when we are trying to transmit this digital data, we need to first convert this data into analog domain, which is, so this is a digital data. Needs to be converted into analog domain. For example, some analog voltage. And this is achieved with the help of a block called digital to analog converter. Okay. And now this V in signal, we need to translate in frequency so as to feed it to an antenna. So here we can add this multiplier block, and this multiplier, as we remember, is taking V in and multiplying with a periodic signal, and this periodic signal needs to be generated by a self-driven circuit. Okay, so this such a circuit is also called as an oscillator, which can generate this signal at some specific frequency, let's say omega naught. And once the signals are multiplied, what we can do, we can one way directly feed to the antenna. But let's just add one more block here. So if you want to transmit the signal to a longer distance, you may want to add more power before feeding to the antenna. So let's add a block which is going to amplify the input power to a higher value before feeding to an antenna. So this is also called as power amplifier. And sitting here, where we have a multiplier. So this is doing the multiplication. And this multiplier is taking input from V in and the oscillator. So this entire arrangement is called mixing operation. Okay, so this is mixing the input signal with the oscillator signal and feeding to a power amplifier. Now we can see the transmitter which we started earlier has got few more blocks, and for still it has some practical issues, but we will come to that later. But now you can see that this simple transmitter will be able to convert digital data and convert into radio signal at high frequency. So now let us look at the receiver in the same way. We try to realize a simple receiver. The simplest form a receiver can be, you can receive the signal which is transmitted by the transmitter with the help of an antenna. And as we have seen earlier, since all the signals are going to be in the digital domain for processing, so even when we are receiving signal at the receive node, the signal needs to be digitized. And this digitization can be done with the help of another mixed signal block, which is called as ADC, or analog to digital converter. Okay, so now you can see the simple receiver which we have designed is taking the signal from the antenna, and the signal is digitized and converting into a digital domain. A very simple receiver. So in the receive mode, as we have seen here, it is going to receive signal not only from the transmitter which is intended, but also from many other transmitters which are present in the same wireless channel. The reason being, this wireless channel is shared. So in the shared channel, there may be a transmitter transmitting signal for a different receiver, can also create electromagnetic signals which can be received by our receiver. Okay, so this is what we want to do, where the intended receiver, let's say, or the intended signal is this one. But in addition to that, we are also receiving lot of undesired signal. Okay, this is the desired signal. Now, how does it affect our receiver performance? Okay, right now we have a very simple receiver. So to understand this behavior, we need to also look at the strength of the signals and what all frequency components do they carry. So if you look into the frequency spectrum of all the signals which an antenna can receive, you'll find that we have some signals here. Okay, this one, this is what we want to receive. But in addition to that, we have signals which are very different frequency, can be very strong, okay, or can be of similar strength very close by. So it is possible that we may be receiving a lot of signals which are not desired in addition to our desired signal. So as to simplify this problem, already government controls who can transmit signal in a given frequency range, and also it puts a limit on what is the maximum amount of power which can be transmitted in that given frequency band. So accordingly, the entire frequency spectrum is split into different chunks of frequencies called as frequency bands, and within this frequency band there can be different wireless standard which can be applied and which can be predefined between the transmitters and receivers so that they can communicate using the same standard. These are the frequency bands. For example, when we are talking about, let's say, cellular signal, so it is possible that one band may be assigned to one operator and another band is assigned to another operator. So as to make sure that the users who are present in this under these different operators can actually can be efficiently allocated different time slots and different frequency channels, so as to not create any interference for operators or the users in different frequency band. Hmm? And most of the time, these frequency bands are further subdivided into small frequency channels, and within this frequency channel there may be so one of the frequency channel which may contain the desired signal, while other frequency channels may contain some unrelated signals which are still sitting in the same band. In addition to that, you can have signals which are out of your band, and depending on the standard which is being followed by different bands, you can have different power levels. Okay, so these are frequency bands, and then here you have frequency channel, and now you can easily see that the design of receiver can become really complex because it may be receiving signals from different frequency bands, but at the same time its desired signal can be much weaker compared to the signal which are present in the other frequency channels or other frequency bands. Okay, so when we talk about receiver design, we need to remember that signal it is receiving from the wireless channel can contain signals from various transmitters, okay, because it's a shared channel. Shared channel. So, what is challenge? Okay, let's try to understand that. So, if we are receiving these multiple signals, what we are saying is we are going to digitize this, and finally we will do the processing in the digital domain. So, one solution you can easily propose that, okay, why not just digitize all the signals together, and once we are in the digital domain, we can separate the signals based on their frequency. So yeah, so that is correct. So if at all we have a very good ADC which can digitize all the signals without losing any information, this is very much possible. But if you look into the ADC design, you will find that this requires the ADC to have very high dynamic range. Dynamic range means it should be able to process or digitize a very weak signal while also processing a very strong signal. Okay, so you can see the power levels can be pretty high. Can be easily several orders of magnitude different, and the ADC should still perform the job satisfactorily. Hmm? To understand the challenge in this such a ADC design, let us look at the input-output relationship of a simple ADC. Let's say this is your V in and this is your D out. So, on the x-axis, I will change the voltage, and on the y-axis, I will plot the equivalent digital code. Hmm? So what happen? Let's say if it is input voltage within some range, this as a result of the quantization present in the ADC, this voltage which is between uh, these two small values may all correspond to a digital code of 0. Okay, and once this voltage exceeds some threshold, then it may be assigned to digital code 1 and higher digital code and so on. Okay. Similarly, the voltage reduces below a value, then it will be assigned a corresponding digital code. So here we can see that as the input voltage increases, the corresponding digital code also increases. Now, if we want to design our ADC to process the input voltage, we need to make sure the input voltage is able to cover this entire range, the entire input dynamic range of the ADC. For example, if the input voltage is very small, for example, it is only creating change which is within the LSB of the ADC, then you can see that if the input voltage corresponds to only the one LSB of the ADC, it is not going to even create any change at the digital code. So entire information is going to get lost. So if at all we want maximum information of input to be preserved, we need to make sure the input signal uses the maximum range possible at the input of the ADC. So the idea is that let's say this is the Vn. Okay. So as time it is changing and this we are. So Vn should cover the entire input dynamic range of ADC to minimize information loss. And since we may not be knowing beforehand what will be the signal of strength received by the antenna, because depending on the distance of the transmitter, accordingly there will be more or less loss in the propagation. So we may be receiving some signal which will be within some range, but we may not know its exact value. And if we want to minimize the loss of information while doing the digitization, we need to ensure that when the signal is being fed to the ADC, before that we add some kind of variable gain. Okay. So this is also called as variable gain amplifier. Then we are going to digitize. Okay. So the simple receiver which we were discussing earlier has now got one more block, which is a VGA in addition to the ADC. So I hope now this point is clear to all of you. And the moment we talk about a variable gain amplifier being added in front of the ADC, okay, we have to now be careful about a lot of issues. For example, we may want to maximize the input signal swing at the ADC, but since our channel is or the signal which is going to be received may not just have our own signal, it may also have signals from other transmitter, which can be much more powerful than the desired signal. Then when we are trying to amplify our signal, the undesired signal may get actually amplified by the same amount, and overall it is possible that their swing may exceed the dynamic range of the ADC which we are looking at. So the presence of the VGA and its operation actually can cause big issue with the ADC itself. And what happens? Okay, so what happens when we exceed the dynamic range of the ADC? Then ADC will cause clipping at the output, and again, because of the clipping operation, we'll be losing information. So, how to avoid this? So, if we come back to our spectrum picture, we can see that cannot start transmitting at the same frequency because you have to follow the wireless standard. So as a result of which there will be always separation between these signals in frequency domain. And if there is a difference between the frequencies, then what we can do, we can add selective gain to the signals based on its frequency, and such a block is also called as filter. Okay, so what we have to do is we have to add a filter which will make sure only the signal which we want gets amplified and any other signal which is out of our frequency channel is not amplified. So if we can apply such a filter, it should do the job. So if we look at the picture carefully, we will realize that depending on where the signals here the amount of relative strength those signals can have also will vary. For example, signal which is in a different band can have much different power compared to the signals which are in the same band. So these kind of signals which are going to interfere from a different band are also called as out of band interferers. So these are out of band interferer. Okay. Whereas, so this is the desired signal. Whereas the signals which are in the same band but in a separate channel are called as in-band interferer. In general, the in-band interferer will be weaker compared to the out-of-band interferer. But again, the difficulty is the in-band interferer can be very close to the desired signal compared to the out-of-band interferer depending on the situation. So first thing what we can do is we can at least try to get rid of this out of band interferer because they are very, very strong compared to the in band interferer. So if at all we are adding some kind of filter, what we can do, we can put a band pass filter to only allow in band signal. Okay, and we can reject all the out of band interferer. So this block is going to give this kind of frequency selectivity. This is a band pass filter. Needed to reject. Okay. Out of band interferer. And this output, we are going to feed it to the VGA, assuming the VGA is going to handle in-band interferers. And then we are going to feed it to the ADC for a digitization. Okay. So now the simple receiver which we started with has got one more block. This is a band pass filter followed by VGA and then ADC.